In this video, we're going to do an example of scheduling a task processor problem on a time schedule using a priority list. And for the rest of this chapter, this is pretty much the same thing we're going to be doing. What's going to change next week is finding the priorities. How do we do that? But that's a question for next time. With the remaining part of lecture in chapter 8, what I wanted to focus on is how do we actually do it, and how does the priority list make a difference? But let's look at the example, and then we'll work on it and focus back on all the terms from chapter 8 in a minute. So immediately preceding the launch of a satellite into space, last-minute system checks need to be performed by the onboard computers, and it is important to complete them as quickly as possible for cost and safety reasons. So, we're going to launch a satellite up into space. The computers need to do a bunch of things to make sure it's not going to blow up or whatever. And obviously we want to get those done quickly because there's a bunch of people waiting on it to happen. And if something goes wrong, obviously there's millions or billions of dollars up in smoke. So suppose that there are 5 system checks that need to happen. That's probably actually way, 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 way more. But suppose there's just 5. Task A, B, C, D, and E with amount of time in parentheses representing the hours it takes to finish each system check. So each one of those could be a series of many things as well. In addition, there are precedence relations. D cannot be started until both A and B have been finished, or as we can see, we've been provided with a digraph, which will often happen. So you don't have to necessarily make it yourself as we did before, but now hopefully we get an idea of what this means. A, B, basically, yeah, it said D cannot be started until both A and B have been finished, and E cannot be started until C has been finished. Again, we cannot violate that because we're assuming this is a critical set of, or like a set that if we do them out of order, say we do E before C, it still could blow up, and we're not solving the problem right. So we have to follow this. This precedence digraph cannot be violated. Then let's assume that there are 2 identical computers on board of this satellite, P1 and P2. It's common that for the book to use those to label, okay, we got our processors. So like if we're going back to the automotive tech example we talked about before, we could have 2 workers, person 1, person 2. And when we're actually building a time schedule, basically we're going to have a time strip for each of them. And on this, we're going to put like, okay, it's going to do task A here and task B here, whatever. And each strip could be the number of computers. But, in a modern computer, it might have way, way more than 2 processors. You could build a time strip for each processor separately if needed. How do we use the priority list model to create a schedule for these processors? That's kind of the question. That's what we're going to be answering in this video. But for starters, we need a priority list. Suppose that the priority list is given by listing them in alphabetical order. So basically, let's look at a randomly chosen priority list. Say we have no idea what order we'd like to prioritize. We're just going to do them alphabetically. Let's see what happens and talk about the issues that come up when using the priority list model. So if we're actually following the priority list model, if you read section 8.3, there's a lot of detailed information about how to do this, but I don't want to walk through each little step. We're just going to do it intuitively and talk as we go about the necessary requirements. But what is the priority list? Notice it's a list of the tasks A, B, C, D, E, which just basically what this is going to mean is we're going to complete them in this order if we can. Notice that we can't necessarily do it exactly in this order because of the necessity. We're not allowed to violate this, but we're going to do basically it's a guideline. We're going to follow this, always scheduling the highest priority task first if possible. But notice in this case, and so for notation, what we're going to do is we're going to circle any tasks which are ready, meaning ready to go. So like if based on looking at the digraph, I can see tasks A, B, and C are ready because they're on the left. They have no prerequisite tasks besides the start. So what we could do is we could circle those. Let me use a slightly finer pen as being ready. And what I'd also recommend is that you circle them on the priority list, which just lets you know when you're working on the problem that I am allowed to do those because they are ready. And notice that D and E not being circled means I'm not allowed to do those because I haven't finished the tasks that need to happen first. Like say I were to schedule E right now, it might blow up or whatever. Again, I'm just going to use that as a joke, but stressing the importance of not violating this. But now that I know what's ready, what I'm going to always do is I'm always going to schedule the first ready task on the first available processor. So since I have two computers on board, task A is the first ready task. I'm going to just schedule that on processor 1. So task A, and in here I have it pre-built so that we can use each of the little tick marks as our blocks. But I'll go ahead and fill in 6 blocks for A. And I like to use colors and and as I'm shading these in, just to help visualize and make it a little bit nicer looking. But we've got task A, and that's going to take 6 blocks. Or you could even, because a lot of the time you're not going to have this time strip available, and you're going to need to draw them yourself. Just basically build a block and make it big enough to encompass the processing time of that task. And also, when a task is in progress, which it is now because I've assigned it to processor 1, we usually use a single slash to mark it's currently being worked on, but it is not done. And then once it is done, we exit out as well. You could do that above on this if you want. I'm not always going to do it everywhere, but trying to keep it all together and focused is very important. And when you start working on these in the homework and online, I promise you these are frustrating. These take a lot of work and a lot of practice. And it's taken me many, many semesters to be able to organize my lectures in a way that makes these problems as easy as possible. But anyways, additionally, we have the onboard computer 1 working on task A. Meanwhile, processor 2, we can have work on the next task. So we're going to continue to schedule tasks as much as we can and from left to right, which now, since task B is the next highest priority, we can have processor 2 work on that, which will take 5 hours. And so I'm going to shade in 5 blocks, I guess using, say, blue instead. Oops, that's too far. And we could outline that. If we were building our own time schedule, we just use build blocks of approximately the right size. Another thing I like to do is at the top and bottom of my time strip, add up the total amount of time that's passed, like with a timeline, how you would normally do that. Just because another goal is to figure out the schedule and figure out the total time, and make sure that it's lined up, because we don't want the task to become out of sync, and we want the flow of time to be evident, which we can see if we're continuously adding it up. So next, we'll see is the next highest priority task, and it is ready, so we're going to go ahead and schedule that one next. And the order that you assign them to, this might not be obvious, but you're always going to assign it to the first available processor. So seeing how I've scheduled it here, I'm not going to put C on processor 1, because notice that processor 2 is finished with its task first. So whichever processor is open, you're always going to schedule whatever task comes next on that processor. So basically C is going to go right here, because if I'm imagining this, processor 1 is going to take 6 hours to do its task, processor 2 is only going to take 5 hours. It'll be done first, so it's going to get the next task, just for the sake of efficiency. So next up, it's going to work on C, which is going to take 7 hours. So again, I could block that off. 1, 2, 3, 4, 5, 6, 7. And I guess we'll use green or something. And I just like to use color because I think it's a little bit easier to see what's happening, and understand that as well. And notice that also what I forgot to mention is that B, once it's finished, like at time 5, we would mark it with an X. And another thing that's very specific to how your online homework will ask you what's the correct priority list for this point in time. Like it always depends on what point in time. Like for example, I could ask you what is the state of the task at hour 5? And this would be the exact look of it at hour 5, because task B is finished, task A is in progress. Actually, I would say you could mark task C is in progress, but at this exact point in time. But notice it would change. Like if I move to hour 6, then A is completed and it would look a little different. So the processor list with the markings is going to look different at each hour of progression through the project. And I usually just mark it as I go. like this. But those questions are a little tricky. You have to actually schedule the project up until that time to figure out what makes sense for those multiple choice questions. Anyways, then now, again, basically, we're going to keep working. So next up would be task D, because I've scheduled A, B, and C. But the problem is it is currently not ready. And additionally, as you're working on these projects, it's important to pay attention to when a task becomes ready. Because task D had to wait on A and it had to wait on A and B to be completed, which notice at time 6 it is, both are complete. So task D becomes ready at that point in time, and we are now able to schedule it. So D is going to take 2 hours. Cool. Grind that out. Use purple or something. And then after 8 hours, that will be done. C is still in progress though, so I don't want to X that one out yet. And notice that it doesn't necessarily, they're not going to get X'd out in order, because as I said, the priority list is a guideline. You can't necessarily follow it perfectly. What you must follow perfectly is the chart up here. And just use the priority list as what am I going to do next as an outline for that. And so now D is completed. Cool. And last but not least, we have to do task E. And you might be tempted to just say, okay, I'm going to slot task E in here, but this is something where it's not necessarily going to work. And every time you're assigning a task, you have to think about, does this make sense? Is this going to work? But notice that I have not circled E yet, and E had to wait for task C to be finished in order for it to be scheduled. And since task C is still in progress, I'm not able to start working on E yet. Again, it could blow up because C is not done. So basically, I'm going to have to wait until C is done. Then at that point in time, which would be after 12 hours, then C would be finished. And now I could work on E would become ready. And then I would schedule E on processor 1. It technically doesn't matter because both processors we're assuming they're versatile and uniform, but you just always put it on the first available processor. Since they're both available, we're just going to put it on processor 1, though it doesn't matter really. I'm just going to follow the procedure, which would be go right here, and this would be task E, 5 hours. And then that one's done. Once they're all finished, we're done with their project. And so I'll go ahead and color in E with, say, yellow. And cool. And that would be at 17 hours. And this would then give us the finishing time of our project. And the book often labels that by saying fin for short. And we're done. And so that is an example of using the priority list model to schedule it. What you also might notice is we have some gaps in our schedule. And often how I'll label them is I'll kind of X them out and put idle time here, and what idle time is in a project is just a time in which the processors are sitting around not doing anything. And if we're thinking about the efficiency of this solution, this is not a very efficient solution, because what we're telling is, well, our computer number 1 to sit around and wait for 4 hours, and our computer number 2 to sit around and wait for 5 hours. That is obviously probably not the best way we could do this, and this solution is not very good. But coming back to our answer, we have followed the priority list model. This is the correct solution when using the priority list and the diagraph together. Also, if you and your friends are working on these problems, you should always get the same answer. It's a very specific process that if you follow it has a right answer. And mistakes would be scheduling a task accidentally not following the priority list correctly, or say, for example, scheduling a task before it's really ready. And those are just it's not quite following it correctly. In the next video, we will examine what happens if we change the priority list and how does the priority list affect the answer. Because in this one, we just were looking at it using an arbitrary list alphabetically. How can we develop a better priority list, and how does that affect our solution?